on the form of the earth, which was an introduction. Now we will go a little bit more in detail. Let's uh, go to the lesson. This is a concept which we learnt, and we learnt it in our previous lesson. We will go through it once again. Terminology called departure. What is departure? The distance between two longitudes along a latitude is called departure. We learned that the distance when measured uh, uh, along a latitude it remains uniform, but when the distance between two longitudes when measured along a latitude, it varies because of the curvature of the earth, which tapers at the poles. And we also learned that it varies as cos of the latitude, where is at 0 degrees cos 0 is 1, and as you go towards the pole cos 90 is 0, and the distance varies as the cos of the latitude. So to put it formally, departure I could term it as change in longitude into cos of the latitude. Okay, let's learn another new terminology called convergence. As we explained, all the longitude, uh, because the Earth's spherical surface, and we have defined longitude as such that they all converge and converge towards the poles. And at any latitude, along a latitude, you will find that there is an inclination between the meridians. This inclination is called the convergence. Here I have magnified the area along the equator just to make the concept of convergence very clear. Theoretically speaking, this absolutely at the equator where the longitudes cut, it should be cutting the equator, that is the mid latitude, or at 90 degrees to each other. In fact, all the longitudes will cut the equator at 90 degrees to each other, which is what I have shown here. And as you go towards the north or south, there is going to be a inclination or a tilt towards the pole, which is going to take place, and which is what we defined as convergence. Terminology which we are going to learn is called the convergency, which originates from our previous term which we learned, convergence. It is a measure of convergence, you can say, to put it in very simple terms. The inclination between two meridians is defined as the convergency. And I have shown in this picture two places on the same latitude, place A and B on the same latitude. What will be the convergency in, if you measure between these two? It will be the difference in their longitudinal measures. That is change in longitude. If one place was 10 degree east, the other one was 04 degree east, then the change in longitude is 30 degrees. So convergency will be 30 degrees. Now, if these 2 points A and B were, if they were not to be on the same latitude, then the convergency of those 2 points would be measured as change in longitude in sine of the mean latitude. This is just a formula which we just need to remember, and that's about it. Okay, let's move on. The lesson is going to get more and more interesting. And before I get on to the further definitions, I just want to introduce you to the concept of charts. As we learned, the Earth's surface is spherical, and but the pilot sitting in the cockpit has to use paper charts and paper maps to carry out the navigation solutions and navigation navigating the plane. So, and we also learned that there are several challenges in presenting a spherical surface to a flat surface uh, in the form of maps and charts. Uh, there are going to be a little bit of adjustments here and there for the before it gets converted onto a chart. That means the measurements on the spherical Earth surface, before they get converted and presented on the charts, there are going to be mathematical modifications to several parameters. Anyway, let's get on to the two more definitions: the great circle track and the Rhumb line track. A great circle is the shortest between, if you were to draw an arc between 2 points, the shortest arc, that would be a great circle arc or the great circle track. However, a Rhumb line track is a track uh, which will follow a uniform compass direction between two places. It's not going to be same as great circle because it's going to be curved. And why? Because of the convergence which we have seen. Here in this picture, I have depicted a chart in which the green line is shown as a Rhumb line track, and the purple line is shown as the great circle track. I it's here it is representing on the Earth's surface, and it is particularly in the northern hemisphere. It's for that reason you will see the great circle as a straight line uh, and a Rhumb line track which is curved to the south and meeting the other place. So this is what is the difference between the great circle and the Rhumb line track. Once again, I wish to point out that this particular picture has been drawn on the spherical Earth's surface. Now, how it is depicted on a two-dimensional paper is what we are going to see as we go on further lesson. Another definition, the conversion angle. We learnt about great circle track and the Rhumb line track, and we also learnt that the great circle is the shortest distance, but you to follow that you have to constantly keep changing the direction. Whereas a Rhumb line track is a single direction track. That means you have to maintain a single direction and you will reach the other point. Here, the angular difference between the great circle track and the Rhumb line track is called the conversion angle. Here, once again, I have shown in blue color the Rhumb line track, which will cut all meridians at equal angles. And of course, the great circle track is a straight line track as shown in green color. So the angular difference between these two is called the conversion angle. Let's get on to some real mathematics and some derivation. Here what I am trying to do is to derive a formula for the conversion angle, or the find out the relationship between the convergency and conversion angle. So let's go through this picture carefully. AB is a longitude, CD is a longitude, and of course a straight line which is being depicted, EF. and the same EF is shown as is the great circle track, and the Rhumb line, which is shown in the green, is uh, touches these two places between E and F. Now at point E, the Rhumb line track and the great circle track, we learned that they cut each other, and the difference between these two is called the conversion angle. Therefore, I have drawn a tangent along this curve at point E. Therefore, angles FEG will be the conversion angle. Similarly, at the point F, the angle EFH will be the conversion angle, since once again a tangent has been drawn at the point F. Along the Rhumb line track. So that works out to be the conversion angle. Now what I have done is transpose this AB once again onto the point F, which is parallelly, I have named it as A dash and B dash. So therefore I wish you all to spend some time in trying to understand this picture. That is the conversion angle, the Rhumb line track, and the great circle track. Once again, EF is the great circle track and a Rhumb line track which cuts these two meridians AB and CD at equal angles, and FEG and EFH are the conversion angles. Let's move further. I'm going to go through the steps a little bit slowly so that you can follow the derivation. Here we are just trying to derive a expression to connect between the convergency and the conversion angle. Okay, this is where we left this diagram. Now the Rhumb line track has been depicted, and as I told you, this AB longitude has been transposed on the point F to form this line A dash B dash. By definition, Rhumb line track is the AEG is same as CFJ. That's how the Rhumb line has been defined. That means this curve is cutting the point E and point F at the same angle. That's why it is called the Rhumb line track. Okay, therefore, angle AEG is equal to angle CFJ. Now, let's get to the other side here. Angle A dash FJ, angle A dash FJ can be written as the total of, that is the A dash FK minus JFK. Simple, it's two angles. One is one subtracted from the other. It's very simple geometry. So the left side I have written as angle AEF plus angle FEG is equal to angle CFA dash plus A dash FJ. A dash FJ. Now, since we already derived an expression for A dash FJ, we can replace this expression. So, which is what I have done. So, I replace this A dash Fj with A dash Fk minus JFK. So, now angle AEF plus angle FEG equal to CFA dash plus A dash FK minus J dash FK. But angle AEF would be equal to angle A dash FK. That's again by geometry. So we are able to cancel these two from both the sides. Therefore, we get angle FEG plus angle JFK is equal to CFA dash. Since we have transferred the minus angle JFK from the right hand side to the left hand side, which works out both to be as conversion angles. So twice conversion angle works out to half convergency. Let me summarize it once again. The relationship between the conversion angle and the convergency is conversion angle works out to half convergency. That's what we derived. The derivation per se is not very important, but just to give a mathematical derivation expression, so we arrived at this relationship called conversion angle is half convergency. But this formula is important, which we will be using in all our numericals. Okay, such concepts could be clarified by solving some numericals, and I will request you all to solve some more numericals to understand the concept. Let's get on to question number 1. A bears 0.79 degrees Rhumb line from B. What is the bearing of B from A? Now, since we, by definition, Rhumb line tracks are constant bearing tracks from either way, so there is no difference. So it's just the reciprocal. So B will bear 259 degrees from A. Let's get on to the question 2. A bears 090 great circle from B. Convergency is 4 degrees. What is the bearing of B from A in the northern hemisphere? Now I have tried to make a picture, but this time it's a chart. Therefore, the Rhumb line is depicted as a straight line and the great circle track is curved towards the northern side because it's in the northern hemisphere. This is one thing which we need to visualize more carefully. So let us go on to solving the problem. Here I have shown the curved one, which is the great circle track as 090 degrees. Now, since we know convergency is 4 degrees, conversion angle is 2 degrees. Therefore, the Rhumb line track will be 2 degrees greater than the great circle track because it's as per the northern hemisphere. It's from the picture also it is clear. So before solving such numericals, it's best to draw a diagram like this and then get on to solving the numerical. So now we know the Rhumb line track is 092 and the Rhumb line track from B to A will be 272 because it's exactly reciprocal. And if you want to find the great circle track between B and A, then it is going to be 2 more degrees from 272, that is 274, because the great circle track lies accordingly in the northern hemisphere. Have a look at this very carefully for another few seconds so that you will be able to understand clearly. Another numerical to sum up the lesson and clarify the concept. Little bit more elaborate and I will go through deliberately slowly. The question is like this. Great circle of bearing of B from A is 0.95. Rhumb line bearing of A from B is 273. What is the conversion angle? In which hemisphere we are in? And what is the great circle bearing of A from B? Now, as I told you earlier, for solving such problems, we must draw both two diagrams in this case. One for the northern hemisphere and one for the southern hemisphere, which I have already drawn. And a straight line in the northern hemisphere between A and B depicts the Rhumb line track, and the curved line which is curved to the northern side in the northern hemisphere is the great circle track. And similarly, in the southern hemisphere, the straight line is the Rhumb line track between A and B, and the curved line to the south depicts the great circle track. So let us get on to the numerical further. Now we know that the great circle bearing of B from A is 0.95, which is what I have depicted in both the diagrams, both in the northern hemisphere diagram, which is touching up to the curved line to the north, and then in the second picture it is touching up to the curved line to the south. Now we know that Rhumb line bearing of A from B is 273 degrees. So which is what again I have shown the angular difference between the meridian and the straight line at B, at the straight track at B. Both have been shown in both the diagrams. I have shown it as 273 degrees. Now we know that angular difference Rhumb line track between A and B would be 0.93 by definition, which is now I have shown in both the diagrams. Now if you study the northern hemisphere diagram, the Rhumb line track is 0.95 and correction, the great circle track is 0.95 and the Rhumb line track is 0.93, which lies further to the right of the great circle track, which is not possible. So therefore the place is not in the northern hemisphere. So now we understood that the places are in the southern hemisphere. Now let us get on to solving the last portion. Now that the Rhumb line track is 273 and 0.93 is the reciprocal, and the great circle track is 0.95. So conversion angle is 2 degrees by definition. Therefore, 273, which is the Rhumb line track, and we need to find the great circle bearing of A from B, which lies left of this track. Therefore, we have to subtract 2 degrees. 273 minus 2 is 271 degrees. Therefore, the answer is conversion angle is 2 degrees and we are in the southern hemisphere, and the great circle of bearing of A from B is 271 degree. We need to solve several numerical before we fully be clear on the concept. I thank you all for having gone through this lesson. Once again, I request your critical comments on the mail ID given below, and please follow my channel on YouTube and my website for more lessons, and I will appreciate if I receive more critical comments. Thank you all for going through the lesson once again.